Lecture is on the solutions of non-linearly separable problems using multi-layer perceptrons. Instead of writing big term like multi-layer perceptron, I just use the abbreviation MLP. So this is what we are going to discuss today, but before I go into the actual topic of today, okay, which is not going to cover too much of a time, before that I should continue the unfinished discussion which we had in the last class related to the debate regarding the batch mode versus sequential mode of processing. And then we will also spend a little time to discuss about the stopping criteria for the backpropagation algorithm, and then we will go over to the actual topic of today, that is solution of non-linearly separable problems. In fact, that is one of the reasons why we rejected the single layer perceptrons and went in for the multi-layer perceptron, because single-layer perceptrons were unable to solve the non-linearly separable problems. So even we saw that the simplest one, that's to say the exclusive OR problem, could not be solved using single-layer perceptron. So at least we should spend some time to explore that if the exclusive OR type of problems, okay, ought to generalize it further into any non-linearly separable problems, whether that can be solved using multi-layer perceptrons or not. Now, the debate that we had initiated in the last class, that is batch mode versus sequential mode, I think general feeling came from the class that the sequential mode is preferred. Okay. I can see that there are some reasons, okay, which led to such kind of thinkings, okay, in the mind of the students who were present here, and maybe that some of you who are distant viewers also got a very similar kind of a feeling that, I mean, as if to say that the sequential mode is good. The thing is that there are certain points in favor of the sequential mode of learning, no doubt, but there are also some favorable points in favor of batch mode of learning. Okay, let's not ignore that. First of all, before we go into the debate, there are two other aspects that should be considered. First is that in the case of the sequential mode of learning, okay, what we said is that we will be doing the weight adjustments on a pattern by pattern basis, right? So we will feed one pattern based on the error that we receive. We adjust the synaptic weights for the entire network, okay, and then we feed the next pattern, okay, as well as the desired output, and then we see the error, then we readjust. That's how it goes, okay, on a pattern by pattern basis. Okay. Now, when we complete all the patterns, okay, like this, we will be completing one epoch of training, right? And then we have to repeat that epoch in a very similar way, okay, again starting with some pattern. Now, the question is that the order in which we had placed the patterns during the first epoch, let's say, the question is that is it mandatory that the same ordering of pattern should remain in the subsequent epochs also. Okay. Apparently, we tend to feel it this way that I mean the same ordering should be maintained, but really speaking there is no hard and fast rule, because after all what you are seeing in a I mean sequential learning, which depends on the instantaneous value of the error energy, okay, it is only the I mean instantaneous value of energy that we are taking, and the weight adjustments that are taking place is happening because of some agglomerated effects of all the past patterns that we have fed, right. So really speaking, it doesn't matter that in order to create that agglomerated effects of weight adjustments, okay, I mean if you were looking at it this way, that the beginning of the epoch in sequential learning and the end of the epoch in sequential learning, ultimately there is some weight change that has taken place, okay. I mean starting with the beginning to the end, some weight change has taken place. Now the question is that whether that weight change is okay, I mean that weight change is certainly because of some agglomerated effect of all the patterns that we have fed one after the other. So in the next epoch, if we disturb that order, okay, it shouldn't matter. In the end, when we complete the epoch, we should see a very similar thing. Only thing is that if you randomize the order of presentation of the patterns, okay, which is normally done actually, that the order in which the patterns are presented, okay, is normally randomized, so that in the next epoch the patterns will be fed in a different order. The third epoch it will be fed in another different order. So in effect what we are doing is that although in the, I mean considering the agglomerated effect of weight adjustments, we still have very similar thing, but one thing is there, that in that process we are going to make the whole process stochastic in nature, okay. Please understand that it is very much stochastic, because from one epoch to the other, okay, the trajectory that we are going to follow in the weight space is going to be different, okay. I mean maybe that I mean the trajectory path is something that we have got in the first epoch, but of course I mean as we continue with more and more epochs, okay, it will go further towards the minimal solution. I mean if it is I mean already near the global minimum, or if there is no local minimum existing, then the solution would be of course for the global minimum, or otherwise it will be a local minimum, but it will follow some trajectory, and that trajectory may jitter, okay, from epoch to epoch if you randomize the thing. But I mean let us not all the time think that such a kind of jittery trajectory is bad for us, okay. Such kind of a jittery trajectory could be there. In fact, we may tend to feel that as if to say that this kind of a jittery trajectory rather than a smoother trajectory, which in fact we would be getting a much smoother trajectory in the case of batch learning mode, okay. But a jittery trajectory sometimes helps you in the sense that because it is stochastic, okay, it has got a tendency to, I mean for the network to sometimes drive out of the local minimum. You know, if there are some small pockets of local minimum, okay, which requires some energy to drive it out of the local minimum, it may be that because there are some errors, okay, suddenly coming in, the error terms may be at times higher, okay. That is why such error can drive us out of the local minimum. Now such a kind of driving out thing is certainly not welcome when it is a global minimum, but such a kind of driving out, which in turn talks a bit about the instability kind of effect, okay, if I am correct in saying so, okay, that has got some effect in driving it out of the local minimum, and if the global minimum is in the vicinity, then the solution could approach a global minimum. So sequential mode that way has got an advantage if you make it stochastic by making the order of presentation of patterns in an epoch in a randomized way, right? So that is one of the points that certainly goes in favor of the sequential mode of learning. There is another point to consider, that in the case of batch processing, let us look at the batch processing equation once again. Okay. What we are doing in the case of batch processing, remember, is that we are taking a cost function that is nothing but the E average. Okay. We are not making it as E as a function of n, where n is the number of iterations or the pattern number. So in this case, it will be, the E average certainly becomes 1 by 2n. How 1 by 2n comes, that should be very clear to you. Summation from n is equal to 1 to n ej square n. Okay, certainly ej square n is the error squared term for the jth neuron, okay, in the output layer. In fact, it should be a double summation. So here j should belong to the set C, where set C is the set of all the output neurons. So it is summation of ej square, okay, and in fact we have been taking all the time as half of ej square, okay, because the term half is convenient mathematically, since it cancels out the when we take the derivative, then the 2 gets cancelled out with this half. Now because it is half term that comes, okay, for each of these, that being a constant, takes out of the summation sign, and we are feeding n number of patterns within one epoch, right? And this capital N, okay, naturally we have to divide the summation of all the error terms by 1 by n, okay, in order to get an average. So in effect it becomes 1 by 2n of this term. Okay, so this is the E average, and consequently based on this E average we are going to compute the delta Wji, the change of weight, as minus eta dou E average with respect to dou Wij, right? And this in effect becomes equal to minus eta by n, okay, summation of n is equal to 1 to capital N Ej of n to dou Ej of n dou Wji. Here this is a mistake, this should be Ji, right? Because we are considering the neuron J and the connection that exists from neuron J to the other neurons, so definitely it is Ji that we have to consider. Now look at the expression that we have got for the delta Ji in the case of the batch mode of learning. Okay. What is interesting to note here is that we have a term which involves a summation of n is equal to 1 to n. And naturally, in order to do such a kind of a summation, okay, we need to know this information, that is Ej of n and dou Ej dou Wji. This we should know for each and every n. From n is equal to 1 to capital N, we must know everything. That means to say that we must have a storage. We must have a local storage to store these individual terms, because we are feeding one pattern after the other, okay, and when one pattern is taken out and a new pattern is fed in, then we are normally losing that information. So we should not be losing that, we should be storing it in some local memory. Okay, so that's one part that we have to remember, that we have to store individually all these things in some local memory, so that at the end, because this delta Wji what we are doing is at the end of the epoch that we are doing, right? Because indeed that's how we have to operate in the batch mode, because batch mode will have the weight adjustment only at the end of the epoch, not with every patterns in the case of sequential mode. So you need local storage, which you don't need in the case of sequential processing, because in sequential processing you are only bothered about the pattern which is now under consideration. okay, and the memory effect, I mean, indeed, I mean, the two implementation has got a difference in this respect. Actually, both need memory in terms of the weight adjustments. But in the case of the sequential mode, that memory is embedded within the WGI term, because WGI term is accordingly getting updated with every pattern. So, what you are seeing as WGI is indeed the effect of the previous patterns that have been already considered and updated, whereas in the case of batch mode, the delta WGI that you are going to see is only at the end. That means to say that externally we have to support a memory in order to store this term, and then at the end of the epoch we do the adjustment based on this. So, naturally some of the advantages, two advantages that we can cite for the batch mode of learning is advantages for, no, I mean, first let us talk about the sequential mode. The advantages for the sequential mode that we can talk of, firstly is that it is stochastic. I mean, if you assume that the pattern feeding order is randomized, then it is indeed stochastic. So, no trapping in local minimum, or less possibilities of trapping in local minimum, if I am correct in saying so. Okay. The second advantage that we are going to have for the sequential mode is that requires minimal local storage, in fact nothing. Okay. So, these two are advantage, and of course, the simplicity of the algorithm. Okay. The simplicity in fact should attract us. So, sequential mode is definitely, I mean, has got this advantage, which I mean you must have felt intuitively when you said that you prefer sequential mode over batch mode. But now coming to some other factors. Firstly is that look at the cost function of the batch mode. Indeed, this is the cost function, okay, with which we are bothered with, because we are bothered about the training for not one pattern, we are bothered about the training over a pattern set. So, naturally, the E average is indeed a better cost function for us. Now, you can argue like this, that in the case of sequential processing, we are using instantaneous value of the error energy, okay, as a cost function, but ultimately it is some agglomerated effect. Ultimately, it takes into account the effect of all the patterns. Okay. Now, it is true that way. In fact, I mean, just to compare the effects, I should say that in one case you are doing the delta WGI adjustment in with every pattern, whereas in this case the delta WGI you are going to do at the end. Now, are these two delta WGIs going to be the same? Ideally they should, but they are not the same. Now, the question is that which of these delta WGIs is better in terms of the computational consideration. This is better because the cost function which we are taking in this case is the actual cost function that we should have taken, whereas in the case of sequential mode, by simplifying it with the saying that we are doing we are taking the instantaneous error energy, we are making some approximation in the cost function. Okay. So, this is a more accurate representation of the cost function, and that is why this is a more closer solution to the steepest descent. In other words, the trajectory that the batch mode is going to follow is a much smoother trajectory as compared to the sequential mode. In fact, it is expected, okay, even intuitively also, because batch mode already does, I mean, by having E average and delta WGI like this, okay, we are already incorporating some amount of low pass filtering. Follow? We are already doing some filtering on it by taking the process of averaging, and so naturally the filtering looks much better. I mean, the filtering effect is much better, okay, as compared to the instantaneous error energy, which is going to have lot of noisy components, which will result in some jitters in the weight space when it follows the trajectory. Of course, the disadvantage could be is that in the case of batch mode, the minima, I mean going to the minimal is guaranteed, but if it is a local minimum, it will be at the local minimum, okay, because batch mode is not stochastic, okay. So there are some kind of I mean advantage that we can talk for the batch mode also. So the advantages that we can talk in favor of the batch mode are: firstly, that it is a more accurate estimate of gradient vector. And there is another aspect that we haven't really discussed upon. Now remember, I mean, I think we have to go back to our lecture number 1 when we talked about one of the great advantage of the neural network being the parallelization, that you have so many neurons, okay, which can do parallel processing. Now, if I look at the problem like this, if I have a multi-layer perceptron and I have a choice that I can give it a sequential training or I can give it a batch training, okay. From the parallelization point of view, if I had used a batch mode, I have the advantage that I could replicate all these MLPs, okay, so that I feed individual patterns to each one of these multi-layer perceptrons, the patterns that I have in my pattern set. If cost is not a constraint for me, then I will be able to parallelize the computation of all the patterns, because the computation of all the patterns are independent in the case of batch mode, whereas in the case of sequential mode it is dependent, I mean from pattern to pattern, okay. So that is why the batch mode is amenable to parallelization. So this is amenable to parallelization. Certainly this is not an advantage that sequential mode is having. So that is I mean more or less the kind of advantages that each one of these techniques, that is sequential and batch mode, has got, okay. Computationally, of course, batch mode is closer to the accurate estimate of gradient vector, okay, but in terms of simplicity, in terms of requirement of less storage, okay, sequential mode is certainly better. Now we go over to the next discussion that we have in our mind, and that is related to the stopping criteria. Now we have been discussing so long about the backpropagation algorithm. Now one question that might have come to your mind is that when are we going to stop it? How long are we going to continue this, okay, the training as such? Now what is the kind of feeling that I can get from this audience? Let's see that. I mean, if I give you a multi-layer perceptron to train using the backpropagation algorithm, okay, when are you going to stop? Any opinion that you can give?
Zero cost function.
Zero cost function. Good. Any other consideration?
No changes into computation of the cost function.
No change in the?
That is cost function at this iteration and the next iteration is same.
Okay, okay. I mean, no change in cost function. Okay, perhaps your friend has said that the cost function becoming 0, and you are saying that no change, but no change doesn't mean that it is no change at 0. No change could be at a high cost also, okay, or that no change could be a just an accidental no change, okay, maybe that if I continue the pass again, okay, there will be some change, or if I just give some stochastic push to the system, okay, there will be some change, okay. Any other other approach that you would like to adopt? Now you are thinking in terms of the cost function, all right. You could think in terms of the gradient also, gradient of the cost function, because after all, when you are taking the cost function, okay, the best thing will be to take the gradient of the cost function. That's what we are taking, isn't it? So in fact, we are in the W space, the weight vector W, okay, I mean this is in the m dimensional space, and after all what we are doing is that we are making a search in the m directional I mean in the m dimensional space, okay, for a minimum of the gradient. So that's why we are going to find out a solution of W star vector, okay, such that I mean at the point W equal to W star, okay, we must have G of W star to be equal to 0, okay. If we have the gradient to be equal to 0, okay, then we are at the point of minima, okay. I mean of course gradient becoming 0 could be maximum or minimum, but because in this case we are going in the negative direction of the gradient, so naturally I mean the path that we follow is always towards the minima. Now it is not that every time we can reach the GW to be equal to 0, okay. Ideally we should reach, okay, but we may not reach the exact value of gradient equal to 0. So one of the stopping criteria that we can say, I mean from a more practical point of view, that instead of telling 0 we can say that the gradient vector is sufficiently small. So we can say that one of the stopping criteria could be is that when Euclidean norm, when the Euclidean norm of the gradient vector is sufficiently small. Now coming to the second point, which I mean the students present here have already raised, that is to say where the cost function reaches a minimum, or where the cost function as such I mean becomes 0. I mean somebody said that 0. I should say that what we should look for is that the rate of change in the average squared error. Average squared error is after all our cost function. So when the rate of change is sufficiently small, when the rate of change of average squared error is sufficiently small. In fact, I mean we can say that if this is the number of iterations, the pattern numbers that we are feeding, and if this is, or I mean to say I mean even question is that from here to here it is 0 to n, where n is the number of patterns is in an epoch, and then again n patterns, or if you are considering epoch to epoch learning, okay, whatever way you do. The thing is that if this is the, I mean if the y-axis is the error term, okay, which is the cost function in this case, okay. Now what happens is that the learning normally follows a curve like this, and when the learning follows a curve like this, we tend to stop over here, okay, somewhere over here, because we find that beyond this point there is no further change in the error energy. So if you are thinking in terms of zero error, maybe that it's not converging to a zero error, okay, absolute zero error you are not able to get. You are getting some residual error which actually remains in the system. So maybe that if this is the residual error that is going to remain, we can say that the point where the rate of change of the average squared error is sufficiently small, okay, almost equal to 0, or it's not changing at all, okay, from one iteration to the other, from one epoch to the other. That is the point where we should stop the training. Okay, then we can stop the training and use that same network for in a test environment, because ultimately that's what we are going to do with the neural network. Now, some people say that, okay, I mean, these two are very good from a theoretical point of view. Okay, in the first case, you need to compute the gradient, and in the second case, you need to compute the average square error, which of course you have to. So the second approach is definitely simpler as compared to the first one. But one thing which is very much required is that no matter what this cost function is or what the gradient vectors Euclidean norm is, we are going to use the multilayer perceptron only with a good generalization capability. We can say that subjectively we should see that when the backpropagation network, when the multilayer perceptron has got a good generalization capability, that is the point when we should stop the training. Okay. So, some alternative approaches which people have worked out is that instead of getting it trained and going over from iteration to iteration and reducing the cost function, okay, like this, sometimes it may be a better approach that you train it with patterns, few epochs, or I mean some number of epochs you do, okay, you sufficiently train it, and when you train it, in between you stop the network, okay, and test the network for its generalization capabilities. So what you should do is that you should have the training patterns at your disposal, okay, you should also have the test patterns at your disposal. So what you do is that you feed the training patterns, and then once it is trained, okay, for some iterations, you feed some patterns from the test. Again, these test patterns are the ones for which you are knowing the desired output, and you see that how good it can generalize, means whether by feeding the test pattern the output that you are getting is close to the desired or not. If it is close to the desired, then the network already has got a generalization capability, in the sense that it is able to compute correct output for the patterns that it never encountered before, right? If we find that it is not yet generalized, then what we have to do is just to retrain it once more, means just to continue with the training, okay, and again stopping it and then test for a generalization. Okay. Now, sometimes it is seen that by doing like this, okay, for many small scale problem, it is possible to find a quicker convergence. I mean, even though we are not measuring the convergence strictly in terms of a characteristic curve like this, the error versus error versus iterations. Okay, instead of a curve like this, we test the generalization capability. That's also one of the approaches that people take. So these are the some of the basic discussions that I wanted to continue in connection with the backpropagation algorithm as such, right? Before I go over to the non-linearly separable problems, that's the topic for today. Okay, is there any question that you'd like to ask in this regard? Anything pertinent to the backpropagation algorithm? Its batch mode versus sequential mode, stopping criteria. So then I can go over to the topic of the day, that is solution of non-linearly separable problem. At least that's something which we should explore once more, that whether multilayer perceptron can do it. Now let me tell you one thing, that when I said multi-layer perceptron, this time I use the term multi-layer perceptron, I did not use the term back propagation network. Now again, I mean, I have seen that sometimes people make a misconception as if to say that all multi-layer perceptrons are back propagation network only. It's not correct. Okay. Back propagation is an algorithm, okay, whereby the weight adjustment is propagated from the outer layer to the hidden and the inner layers gradually. That is a kind of algorithm which essentially requires the fundamental conditions for a back propagation algorithm to work is that the phi function, the activation function that we are using, that must be differentiable, continuous and differentiable. Okay. So now in the last class we discussed that I mean, some of the typical activation functions like the sigmoidal nonlinearity, okay, in terms of logistic function we already derived that what its derivative is and what the corresponding delta term, the local gradients are. Okay, these things we discussed. But we should also keep in mind that it is possible for us to construct a multi-layer perceptron even with neurons which are having activation functions like signum or McCulloch bits, okay, which are in fact having discontinuous phi functions. Okay. But multi-layer perceptron definition is that any perceptron network arrangement that you are having where there is one input layer, there is one output layer, and there can be at least one hidden layer. But we are not putting any restrictions on the activation functions, whereas in the case of back propagation algorithm there is a restriction on the activation functions that it must be differentiable. So we can just see that whether any multi-layer perceptron, okay, with of course suitable choice of weights, okay, can solve a non-linearly separable problem or not. And the simplest of that which we are going to take is the exclusive OR problem. Okay. So we reconsider the XOR problem, and we had shown in the, I mean, during the discussion of single layer perceptron, that single layer perceptron is unable to solve exclusive OR. Now what that exclusive OR problem is, that we are having two inputs x1 and x2, okay, and we are having a truth table like this where y being the output, okay. When it is 0 and 0, the output is 0, 0 1 or 1 0, the output is 1, okay, and 1 and 1, that is to say when both of them are 1, then the output is 0. Okay. So that means to say that only if just one of these is 1, then the output is 1. That is the exclusive OR problem, which basically means that if we try to see in the two-dimensional space with x1 in this axis and x2 in this axis, this being the 0, this being 1, this being 1 for x2, okay, we are having 4 corners of a square, okay, to which, I mean, since the patterns are 0 0 0 1 1 0 and 1 1, we can feed the patterns, we can keep the patterns in the 4 corners of the square which we have formed like this. Now what we are doing is that I mean 2 out of these, that means to say that when it is 0 1 and when it is 1 0, for those patterns we are going to have the output as 1. So the ones that I have just now marked over here, and this problem, and these two are open circles indicating that they are zeros. Okay. Now the basic problem of linear separability which we had already defined is that we are not able to imagine a line that separates the 0 patterns from the 1 patterns. Okay. In that sense it is non-linearly separable. Okay. But let us see that if we could solve the problem, okay, using the multi-layer perceptron or not. Okay. Now we just take an example of a multi-layer perceptron where let us say that we have got two inputs x1 and x2, okay, and we are going to use only 3 neurons in this, 2 neurons in the hidden layer and 1 neuron in the output layer, all right. Now, what we are going to do is that we are going to connect the x1 and x2 to these neurons, right, to this hidden layer. So, these two are forming the hidden layer, whereas this one is the output. And again, these as well as this should be connected to this neuron. Now, both these neurons will be having some bias, right. Now, these neurons will go through some activation functions. So, let us say that these are the 5 functions of these neurons, okay. And then the activation outputs that we will be getting from these neurons, they will be connected to the output neuron. Output neuron also will be having some bias, and then this is the output that we are doing and we are getting. And here there will be synaptic weights between this connection of x1 to this neuron. Let us say this is neuron 1, this is neuron 2 and this is neuron 3, all right. So, this will be in effect the W11, this will be W12, this will be W21 and this will be W22, okay. This will be the bias B2, this will be the bias B1 and this will be the bias B3, and here it will be, because it is connected from 1 to 3, it should be W31 and here it should be W32, okay. And for the sake of simplicity, I mean, because I do not want into the computation of 1 by 1 upon exponential terms, etc., for which I will be needing a calculator, I will simply apply Macaulay-Pitts model, okay. That looks much easy for me, okay. So, that all that I am going to do is to compute the activations, okay, and then I will be deciding that whether it is 1 or 0. Now, you can argue that Macaulay-Pitts model certainly does not make the network trainable with backpropagation algorithm, okay, because it is not differentiable. Well, I mean, to everything there is an approximation that you can always do, in the sense that you could take a logistic function only, okay, and all that you do is that you put a sufficiently, the a, that is to say the slope that you are having for the logistic function, you make that sufficiently high. If you are making it sufficiently high, still as long as you follow the function as 1 by 1 plus exponential to the power minus a v, that function becomes differentiable and we can more or less approximate that, okay. So, that I mean, it is not correct to say that I cannot train it using backpropagation network. I can train Macaulay-Pitts model with a close approximation that I take a to be quite large for all practicable purposes. And let us say that somebody has trained this network like that and obtained a set of weights as follows. Say that I take W11 to be equal to 1, W12 to be equal to 1, W21 to be equal to 1 and W22 also to be equal to 1. So, all these weights are equal to 1, okay. And I take B2 to be equal to minus 0.5 and B1 to be equal to minus 1.5. The whole idea of doing it is, if you look at these two neurons, let us have a look at the neuron 1 and 2 now. What is the total induced local field at the neuron 1? Let us say, yes, I mean x1 plus x2 minus 1.5, okay. So, the decision boundary is that x1 plus x2 minus 1.5 should be greater than or equal to 0, okay. So, when x1 is, so we go through the truth table, what happens for 0, 0? is the output active or not? I mean, this is McCulloch-Pitts model. So, is the output of this neuron 0 or 1? 0. 0, 0 is 0. What about 0, 1? 0, because the total activation is 1 minus 1.5, which is equal to minus 0.5, less than 0. So, the output remains 0. So, any one of these means that it is still 0. Only when both of them are 1, only when x1 is equal to 1 and x2 is equal to 1, this is having an activation value, net activation value equal to 0.5. So, then it goes 1. So, it is acting as what logic gate? AND gate. So, the neuron 1 is acting as an AND gate. Okay. What is the logic function realized by neuron 2? OR gate. Okay. Yes. Neuron 2 is indeed an OR gate. You just see when x1 is equal to 1, when both are zeros, that time the net activation is equal to minus 0.5, okay, which is less than 0. So, the output is 0. But when any one of them is 1 or both of them are 1, in these cases it will be when any one of them is 1, then the net activation is 1, this one is 0 and this one is minus 0.5. So, it is 0.5 greater than 0. When both of them are 1, 1 plus 1 2, minus 0.5, net activation 1.5, still greater than 0. So, number 2 neuron is acting as an OR gate. Alright. Now, what we are doing is that we are combining the outputs from this AND gate and OR gate into another neuron which is there in the output layer. And for that matter, we have judiciously chosen a weight like this. We have chosen W32 to be equal to 1. Okay, the one which is connected to the OR gate, I put W32 to be equal to 1, and W31 in a very interesting way we make it minus 2. The purpose of doing that is that we are going to make an excitatory connection with W32 and we are making an inhibitory connection, because the weight here is minus 2, we are making an inhibitory connection with this neuron 1 to neuron 3. And if we make things like that, okay, you can now see that when the output of these neurons, alright, when the neuron 1 output is 0, okay, and I took B3 to be equal to minus 0.5. I took B3 to be equal to minus 0.5. So, that when both these neuron 1 and neuron 2 outputs are equal to 0, in that case output is going to be 0, right. When this is 0, but this is 1, okay, the output of OR gate is 1, but the output of AND gate is 0. In that case, what are we getting? We are getting 1, okay, because this is 1, this is 0 and this is minus 0.5. So, this is 0.5 which is greater than 0. So, this will be 1, okay. And when this is also 1 and this is also 1, in that case what do we get? 0, because the net activation is 1 minus 2 minus 0.5, which is less than 0, okay. So, the output will be 0. And when is the condition that we are getting both of the outputs as 1? X1 and X2 both equal to 1, only in that case both neuron 1 and neuron 2 will be having their outputs equal to 1, okay. And only then we are going to have, and in that case we are going to have, okay, no matter what when both of them are 1, that means to say, both of them are 1 over here, then we are getting 1 here, 1 here, and that will lead to output being 0. When both of them are 0, x1 and x2 0, in that case this is inactive, okay, this is having output 0, this is also having output 0, and this is minus 0.5. So, we are again having the output as 0. 0 0 is 0, 1 1 is also 0, and when it is 0 1 or 1 0, in that case this output is 0 and the neuron 2 output is 1, and that will make the output 3 to be equal to 1. So, we got what we wanted. Is it solving exclusive OR problem? Those who are not convinced, please feel free to ask me. Okay. It is very simple to see that. Okay. I mean, I can just repeat it once more. When x1 is equal to 0, x2 is equal to 0, please verify that neuron 1, okay, or to say, I can say y1, okay, y1 is equal to what? Y1 is equal to 0, y2 is equal to 0, and y3 is equal to 0. When x1 is equal to 0, x2 is equal to 1, what happens? y1 is equal to 0, y2 is equal to 1, y3 is equal to 1. When x1 is equal to 1, x2 is equal to 0, then same thing happens. Same thing happens. y1 is equal to 0, y2 is equal to 1, y3 is equal to 1. You can see that. And when x1 is equal to 1, x2 is equal to 1, in that case y1 equal to 1, y2 equal to 1, but y3 is equal to 0. So, in effect, if we are looking at only the table pertaining x1, x2, y3, x1, x2, y3, x1, x2, y3, x1, x2, y3, we are getting exclusive OR solution. So, what a single layer perceptron could not do, a multi-layer perceptron can do this. In fact, if you are looking at the at the two-dimensional space, in fact, the problem should again be posed this way, that we are getting x1 and x2. Now, if you look at the output of the neuron 1, okay, neuron 1 in this case is acting as an AND gate, as you rightly found out. So, AND gate means only when this one, both of them are ones, okay, then only it is active. Okay. So, in fact, its line of separability should be something like this. Okay. In fact, it will be like that. Here 0.5, I mean, because you see the way these weights have been chosen over here, okay, 1 and 1. So, as long as this is greater than 1.5, okay, it is going to give you an output equal to 1. So, here also 0.5 and here also 0.5, and we will be having a line like this, which will separate the patterns of this. So, this will be the case where the output will be equal to 0, and this will be the zone where the output will be equal to 1. So, this will be the situation for neuron 1, this will be the decision boundary. Okay. And for the case of neuron 2, which is following the logic of an OR gate, what is going to be such kind of a decision boundary? In this case, I mean, should it be this side or should it be this side? This side. That is very correct. In fact, again, because we have chosen 0.5, okay, it is easy to see here that both of these are 0.5. So, the slope of the line will be 45 degree, and in this case the 0 patterns are situated over here. The 0 patterns are situated over here, and the 1 patterns are situated over here, because neuron 2 is an OR gate. So, for this one as well as this one, the output is going to be equal to 1. Only for this it is 0, whereas for the case of AND gate, this one and this one, the output is 0, and only for this the output is equal to 1. So, that is for neuron 2. And in fact, neuron 3, coming to neuron 3, it becomes a combination of neuron 1 and neuron 2 in such a manner that neuron 1 is having inhibitory contribution, okay, as if to say it is reversing what the effect it did, and neuron 2 is having an excitatory connection, and finally in the case of neuron 3, okay, the decision boundary that we are going to get is something like this. There will be in fact two decision boundaries, all right. There will be one decision boundary contributed from here, and there will be another decision boundary contributed from here. And in this case what happens is that for for the patterns lying inside this decision boundary, the output is equal to 0. For the patterns lying beyond this decision boundary, the output is 0, essentially contributed by this decision boundary, but everything reversed, inverted, because in effect this is an inverter connection. This is a NOT gate connection if you look at it, from 1 to 3, because it is having a negative weight over here. Okay. So, for these patterns the output is 0, for these patterns the output is 0. So, that means to say that for these two corners, okay, the outputs are 0, whereas for this one and this one the output is equal to 1. So, this is the boundary, decision boundary that we are following from neuron 3, which indeed solves the exclusive OR problem. Okay. So, that is the greatest advantage. In fact, it is easy to train a network like this. Those who are conversant with the programming, okay, can very easily try it out. What you do is that you can, instead of taking McCulloch and Pitts model, you can take linear, a logistic function you can take, and then you can start with some arbitrary weight and arbitrary bias, okay, and train this network, because the exclusive OR truth table you know, okay, and train it sufficiently, and you will see that after training it will be able to classify the exclusive OR patterns, okay, in the desired way. Okay. So, this can be experimented very easily using your own computers. So, that is all for today. Thank you very much.